Right. So we ended up last week with the Lie algebra of SO3, which of course is the group of 3x3 orthogonal matrices with the determinant of +1. And this group can be used to describe the basically the proper rotations. Okay, so very good for a system with spherical symmetry. And from that, you get a fair amount of stuff that just comes from the algebra. I mean, you get a fair amount of this sort of geometric stuff that just comes from the algebra itself. So we started off with the Lie algebra, which I forgot to write on the slide. Sorry, any question? Yeah, okay. I epsilon A, B, C, L, C. Okay, so the very familiar Lie algebra. And I mean, I should mention, just in case there's a temptation to think this is not the only Lie algebra. I mean, there will be other groups with other Lie algebras. Okay, it's just that this one you will see kind of time and time again anytime you have something with kind of a three-dimensional spherical symmetry, and some other types of symmetries as well. Okay. Anyway, starting from this, of course, then we went. If you now look back at the slides, we essentially borrowed a lot of stuff that you guys learned last year, or at least saw last year, with the Casimir operators. This enabled you then to get, infer the existence of a bunch of eigenvectors labeled with L and M being down here. So L ends up being the label for a particular kind of representation space, and M would then enumerate the basis vectors in that representation space. Okay, so that's sort of where we ended up. We also saw that there were, it was just mentioned that we had actually already seen objects which belong to these representation spaces. And when I say representation space, I mean in some sense what we're talking about is things which have not just this local behavior in terms of the relationship between the infinitesimal rotations, but now the global behavior in terms of periodicity. The fact that for just a plain old vector, right, you would actually have to rotate it by a whole angle of, rotate around the axis by 2 pi in order to get back to the original state. But for other things, like the rank 2 symmetric tensors, we saw that if you rotated it through an angle of pi, you would actually get back the original tensor. Okay, so you saw that there were various things that rotated in these different ways. So let's see. Right. Yeah. Gee whiz, keep on skipping. Okay. But in any case, so if you had something which was a composition of several representations, actually. So, you might think, right, because we're talking about periodicity, I guess, just another, sorry, this will seem to go around in circles because it's all referring to exactly the same thing. It's just all from different angles. Because we were talking about the periodicity, actually in that case, then maybe I'll go to this slide just to show it, right? I think I showed this picture last week as well. You would see the L equals 1 needing a 2 pi rotation, this guy pi rotation, two-thirds pi rotation down here. I mean, effectively what this is that it's basically the number of oscillations around your axis of rotation, right? It's the number of nodes. That's right. That's the better way of saying it. The number of nodes in, say, a wave function as you go around your axis. So therefore, that's why there is in quantum mechanics an association with angular momentum. And sort of related to that, therefore, this idea that we were talking about, okay, so now that we're talking about angular momentum, you did have states that could be a superposition of different angular momentum states. That's what you would actually then put into your state vector, which in this case is represented by a column vector with all these amplitudes, right? And then if you now took that state and rotated it, this is what the rotation matrix looks like. It instead of elements scattered everywhere in your matrix, you just have this nice block diagonal form which rotates the L equals 0 part, the L equals 1 part, the L equals 2 part, et cetera, et cetera, et cetera. Okay? Now, this is actually then, if you just think a little bit further, I mean, in fact, I ended, I think, last time where I was going to take an L equals 1 state and sort of make it collide with an L equals 2 state, and then we sort of looked at what the sort of, how you would then, or I illustrated how you would then decompose that, the final state system. Basically, if this interaction has spherical symmetry, right, then you have, then this whole thing becomes rather powerful because you end up, let's see, how shall I say it? Yeah, basically, you still have, now you have sort of like your initial systems with L equals 1 and an initial system with L equals 2. You have an interaction which may have another L, okay? You add all those things together, and basically you still have the ability to rotate your system, in other words, apply a rotation matrix. You can ask about the rotation matrix. And yeah, what you should end up with then is that you will still end up with these same invariant subspaces. Okay. Now, that's just a mathematical way of saying that L stays the same. In other words, the angular momentum, the spherical symmetry is actually resulting in the conservation of angular momentum. Okay. So that's actually one manifestation. This is actually one manifestation of something that we'll later see encapsulated or generalized in Noether's theorem. But basically, this is actually what sort of like the group theory approach to conservation laws in physics. Okay, because now you can just sort of take your system. It has this. All the bits in your system have this symmetry, and therefore your physics. The descriptions of your state, whether in this case it looks kind of quantum mechanical, but really it's also classical. But the important factor is that this state divides up into these spaces which are just rotating, sort of into each other, okay, and therefore maintaining the same values of L. Okay, now, so that's sort of where we ended up. Actually, because that's sort of one little unit. Any questions on this? Okay. Now, as I said, this argument probably seems to go around in circles because actually, we've just been talking about the same sort of thing from a variety of different perspectives, and they all sort of come. They kind of come together in this sort of somewhat mathematical way. Now, should point out, however, we did sort of forget or neglect something, right? Because, in that diagram of spherical harmonics, I was only looking at L value or integral L values, so 0, 1, and 2, and so forth and so on. And of course, that there are these other half-integer things, okay? And you might be kind of wondering, well, how does that fit into this whole picture? Well, from a group theory perspective, it's not difficult at all, okay? Because basically, it's all the same algebra, right? You still have the same Lie algebra. It's just a different representation number or representation label. So if you have j equals 1/2, well, it happens that there's no spherical harmonic which fits into this representation. Okay, but on the other hand, physics-wise, that wasn't necessary, right? Spherical harmonics only ever claimed to deal with the integer elements. Sorry, I keep on switching between L and J because both of them tend to get used. Okay, anyway, but to look at the behavior of this guy, let's just go back to the algebra. We can write down the generator for the for the j equals 1/2 representation. So since we are diagonalizing the third element, this one will simply be 1, 0, 0, minus 1. Okay. And this is obviously a basis, you have basis vectors. If we were doing that sort of, JM notation, then, in terms of kets, you could write them this way. In terms of column vectors, for this basis, you would write it that way. Okay. Right, okay, so what are the other ones? Well, actually, it turns out that these are also fairly well known. Right? And then J2, you will get 1/2 0 minus I 0. Okay? Or in other words, right, where sigma A are the Pauli spin matrices. Okay? Right. So, again, somewhat familiar stuff. And if you do a finite rotation, let's do the easy one. Just around Z. You can of course demonstrate this with other things. Around other axes. And then you apply the exponential map. You get e to the minus I theta J3. Okay, that one's a fairly easy one to do. Obviously, 1 minus I theta J3 minus theta squared over 2 J3 squared, et cetera, et cetera, et cetera. This is just going to be equal to cosine theta over 2 minus I sigma 3 sine theta over 2, which of course makes it quite explicit that you have to rotate through 4 pi in order to get back to the same thing. So, get back to your identity element. Okay. Let's see. Right. Yeah. In fact, what we have described here, right? If you were to write down these these group elements, what you'll actually find is that these matrices, or with the exponential map, these rotations, with j equals 1/2, basically end up being the group of 2x2 unitary matrices. So 2x2 unitary matrices with determinant plus 1. Okay? So what we're finding is that SU2 it can be used as a representation of SO3. Okay? But it is actually, it's not a faithful representation. It is actually a homomorphic representation. Okay? Because in this case, it turns out, I'm not going to work out the details of that. It just takes a little bit more time to do it. But basically, with SU2, you actually have 2 elements in SU2 for every element in SO3. So 2 elements of SU2 correspond to 1 element of SO3. So therefore, we call this, let's see, what we call this is the double cover. SO3. Okay. Now, there will be a certain number of terms that are used to describe this relationship because it's quite an interesting one that people have looked at from many angles. One thing which is kind of interesting to note, remember that because this is a representation of SO3, we are still talking about the same Lie algebra. So it's the same local behavior between elements that are close to each other. But it does have a rather different sort of global behavior. So the periodicity, which we were talking about here, right, actually manifests itself in a kind of interesting way. So let's consider a general element of SU2. Okay, so it's got to be a 2x2 unitary matrix with determinant plus 1. So I'll just write that as A plus IB, and then we're going to multiply, when we're computing the determinant, we'll multiply by A minus IB. We'll do a similar thing with the off-diagonal elements. Okay, so A, B, C, and D are all real parameters. Okay. Yeah. So the determinant of this element is just going to be, well, don't need the mod because they're all real. A squared plus B squared plus C squared plus D squared is equal to 1. Okay? So this is simply, so the parameter space for the SU2 Lie group is equivalent to a unit sphere in 4 dimensions. Okay. Now, I know it's a little bit hard to imagine a 4-dimensional sphere. Just imagine a 3-dimensional sphere and just, kind of just think that there's another dimension there. I don't know. But the thing that's kind of, sort of important about visualizing that is that on this unit sphere, you now do not have all the weird connections that we had with SO3. You remember with SO3, you had this topology, right, where you had, in that case, it was a solid sphere. But one element over here would actually be the neighbor of an element on the other side. Okay? Just because of the way if you look at the parameters, you can just infer that. In this case, it's only the surface of the force sphere. So anything that's actually local in parameters is genuinely local in terms of the infinitesimal rotations. Okay. So, So therefore, we will write somewhere around here, yeah. So SU2 is what we call simply connected. Okay? And in general, because of this simple connection, and the simple connection is actually intimately tied with the fact that, where did we say? Yeah, we have the 2 elements of SU2 corresponding to every element of SO3. That's actually what gets rid of this double connection. Okay? That gets sort of, really into topology, and B2, as I said, B2 is not a course in group theory, and it's even less a course in topology. Okay, so we're not going to go into the details of that, but just take it, you can take it that SU2 is just a better behaved group because what is things that look close to each other actually are close to each other. Okay? Now, just to note, if you start doing things like reading, high energy physics theory papers on, say, let's say every day, should of course always, advocate doing this, right? You know about this website, archive. It's actually where all the physicists put all their, and a lot of other people, put preprints before, on the way to publishing papers. So there's a, high energy physics, phenomenology, and theory preprint servers. You can, enjoy yourself by reading about 50 abstracts a day. And generally every day, there will be an article where someone is talking about the double cover or the simple connection or something along those lines, okay? Because that is actually how important this is in dealing with some of the sort of geometric approaches to physics. Okay. Right. Okay, so one thing that I did want to cover, because now this is actually now we're getting into something which I should say used to be on the syllabus, is not now, and that is the topic of spinors. Okay? Because spinors are the representation space of the j equals 1/2 representation. Okay? Right? I mean, we saw that, in fact, basically, those vectors that we had up there, those are the basis vectors. And you would sort of expect, or at least, in one representation, you might expect a, let's see, what is it, 2 by 1 column vector representation. Okay? That is, if you insist upon, using column vectors. And actually, people have come up with such representations. I think if you look in some Professor Steen's old notes, you will see one where you have, here's your two by one column, complex column vector. This, if you sort of write it out in terms of other parameters. Okay, I'm just going to write them out. Explain a little bit in a second. So cosine phi over, that's a theta, over 2, e to the minus I phi over 2. Okay, and then here you have sine theta over 2, e to the plus I phi over 2. Okay? And so you have real parameters s, alpha, theta, and phi. Okay, so these are all real. These are pretty easy to interpret, right? These are just the angles that the spinor is pointing in. This is a kind of magnitude, I guess. As for this guy, this is sometimes referred to as the flag, in the sense that it is an orientation in this spinor which does not change when you rotate. Okay, so sometimes people will have this little picture of a spinor being sort of, you're kind of like, well, there is a vector here. So with theta and phi, and then there's this little flag over here pointing in some direction, okay, in some sort of orientation. Okay. Now, you might say people put a lot of work into this representation. In fact, I think Roger Penrose wrote a whole book on this topic. I'm not sure how useful it actually is. Yeah, can be used if you want. Now, the reason why I'm telling you this, though, as I said, it's not actually on syllabus, but because it is close enough, you can actually do all the algebra with this. That means it's a prime candidate for some clever examiner to say, let's teach the students something in the middle of the exam. So I'm just giving it to you just in case an examiner does that. So, it won't look unfamiliar. You'll just have seen it before, and maybe you'll have thought about it, and the picture is not that hard to have in your head. Okay. One other representation which I want to cover is actually goes, well, instead of using a 2x1 column matrix, you can actually do a 2x2 unitary matrix. Actually, is it actually unitary? Well, we'll just go with a 2x2 matrix. Okay, because after all, we saw that even though you can always sort of you can always think of these representations in terms of the basis vectors, and therefore it's natural to think of a column vector. The representation doesn't necessarily have to be. And in fact, you've seen things that are a little bit like this because you saw that, for instance, L equals 1, right? And there are L equals 1 pseudo-vectors, which are naturally represented as rank 2 skew symmetric tensors. And similarly, you have your rank 2 symmetric tensor, and that gives you an L equals 2. That behaves as an L equals 2 representation. Okay, so it's not that unusual to see a 2x2 representation. And in this case, I think this is actually a little bit easier to deal with. So we'll just say x, and then we will go back to the summation convention. Okay, so this is the sum over real parameters with Pauli spin matrices, and that will equal this sort of form. Okay, and therefore the magnitude of this will be minus determinant of x. Well, we should say length. The length of x. That. Because some people use the vertical bars to actually designate the determinant, so that's a little bit misleading. Okay, so we'll say that the length of x is going to be minus the determinant. Actually, why did I do? Okay, there's a funny sign convention going on here, which will probably become clear in the second half of the lecture. But anyway, yeah, so you get the sort of typical kind of, minus the distance there. Now, how do these, if you use this as a spinor, as the representation, as your j equals 1/2 representation, how do you do the transformation? Okay, so you have a transformation rule where you say x prime is equal to, your 2x2 unitary matrix in a sort of similarity transform. Okay, and because this is a unitary matrix, you just take the remission conjugate there. Now, you've seen something very much like this, right? This is pretty much the matrix form of a transformation of a rank 2 tensor. Okay, that's not completely coincidental. Sort of like a rank 2 tensor. But I'm going to have to leave you in a little bit of suspense at the moment, because this will become clear, this structure will become just a bit more clear or a little bit easier to understand after we introduce special relativity. Okay? So this will be one of those cases where introducing special relativity will just actually make things easier. Now you can, if you want to, you can of course, do a sample rotation. Let's see. I guess a couple little things that we should just note. Obviously, determinant of x prime is just going to be the product of the determinants here, but these guys are just 1. So determinant of x prime is same as determinant of x. So that's an invariant. Let's see. Sorry, which one? You're right. Thank you for that. Yeah. Okay, and then, right, so let's just do a very quick little rotation. Let's just rotate around the z-axis, in which case, because sigma 3 is simply, as you noted, there's got to be a minus sign here, right, which I forgot. So the rotation matrix, the corresponding rotation matrix will take the form e to the minus I beta. Let's rotate through an angle beta, and it will still be diagonal, so you just get this. Okay? And if you multiply this by, that thing up there, so you just, write it all together, e to the minus I beta, e to the I beta over 2 times z, x plus iy, x minus iy, and then minus z. And then you get your Hermitian conjugate here, so e to the I over 2, e to the minus I beta over 2. Okay, please do check for signs, just in case I have missed one. Okay, but what that should give you in the end will simply be, well, z is going to stay the same. You'll have x plus iy times e to the I beta, x minus iy, and this should be the complex conjugate, so minus I beta, and you still have your z. So you can see that, z stays the same, but you've added a complex phase to the x plus iy combination, which is exactly what you would expect to do if you're rotating around the z-axis. Okay? Okay, so that is your quick introduction to SU2, but I'm just going to add a couple little points here, which we'll do with pictures. Sorry, any questions? Okay. Maybe there will be more. Okay. Now, this has given us as I mentioned, there aren't really, spherical harmonics do not form these kinds of representations. There are generally no sort of nice spatial representations unless you want to really make a convoluted one like the 2x1 that Penrose came up with. So where do these actually get used? Well, okay, fine. In classical mechanics, you tend to need to be periodic within at least 2 pi. Quantum mechanics you can do a little bit differently, right? Actually, that one you can tolerate the 4 pi rotation because, of course, you deal with wave functions, not with, or quantum states, not with the classical states. So, consider an electron in an atomic orbital. To rotate in space, we actually have to rotate, of course, the whole orbital. But whenever you do that, remember, you also have to rotate the wave functions. So the wave function for the electron, the quantum state of the electron, will also have to rotate. So in spite of the lack of a position representation, the spin state still rotates just with the 4 pi rule. Okay? So, if you do your 2 pi rotation, if your electron is in an L equals 1 orbital, this is what that looks like. You do the pi rotation and you get it turned over, and in 2 pi you go back. But the spin 1/2 state, you will actually, when you go through 2 pi, you'll actually end up with a minus sign. Okay? And that is in spite of the fact, as I said, that there is no actual position representation of this electron spin. Okay? These slides will actually be on Canvas, by the way, just if you want to look at it more. Right. This is why the total angular momentum of an electron orbital is actually L plus S, not simply L. Okay, so if you're always kind of wondering why was it, what's the physical basis of having to add spin into the into the orbital angular momentum to get the total angular momentum, this is actually the reason. So you will see this in atomic physics, which in the old days was also taught in Mukama's term, but nowadays you get to teach it next, you get it next term. You may also see this in B4 because this is, of course, how you deal with the quark model. And let's see, yeah, you'll see another current, Dirac-Lagrangian, especially, et cetera. Okay, so in spite of being intrinsic and without a position representation, electron spin is actually a property connected with spatial rotations. Okay, that's in some sense the key thing to remember here. Now, in composite particles, the intrinsic spin is the total angular momentum of the constituents, right? Again, because you are rotating now a composite system, but you're still rotating within all these invariant subspaces, angular momentum is still conserved, for these geometric reasons. So that is going to be reflected in this sort of intrinsic spin of the composite particle. So, of course, the way to look at what's going on inside, you have to go to shorter and shorter distance scales. When you go to shorter distance scales, within this position representation, the orbits start to reappear. So, if you start looking closer and closer and closer, right? Let's say this was an atom or whatever, or maybe a proton. Well, no, let's go with an atom. Then, at some point, you will start resolving the components of the nucleus and the electrons, and you keep on going farther, and eventually you will start looking at the quarks or gluons. Okay. So that's fine, right? That's kind of easy to understand from the perspective of composite particles, but it turns out just because nature is just seems to want to just make life a little bit harder. Fundamental fermions still seem to have an intrinsic spin no matter what we do. Okay, so no matter how microscopic we get our vision to be, it seems that there's always that J = 1/2 representation. Okay, and we don't have the spatial representation. Yeah, let's see. Oh, one other reminder that I do have to mention. The analogy with rotation is so strong that you will actually see this come up in a number of different places. So in particular, there is something, have you seen this concept of isospin in nuclear physics yet? Okay, so isospin is actually a symmetry between a neutron and a proton. Because what people noticed was that in a lot of interactions, you could pretty much just change the neutron and the proton, you could swap them, and it actually didn't affect anything, okay? So all the cross-sections remain the same, all the distributions remain the same. And, so they said, there's a symmetry there. But it's not actually connected with physical rotations, okay? So in other words, in fact, if you say, actually in that case, because it's proton and neutron, right? So you have an amplitude for your proton and you have an amplitude for your neutron. The symmetry group then is SU2 because you can now rotate these amplitudes and the physics stays the same, okay? But, as I said, this will be called isospin in the sense that it is like spin, okay? But it is not the spatial spin. This is only a rotation in proton-neutron or later up quark, down quark space. So if you do a rotation, you do not in fact turn protons into neutrons. Okay, just as a reminder, because this can be a little bit confusing, when people, the word, the word that they use, isospin, is just to tell you that it is acting algebraically like spin. Okay. Right, any questions on SU2? Okay. Yeah, trust me, it's easier. Right, okay. Anyway. Okay, so you can put down your pens because the next part of the lecture is not actually about the Rubik's Cube. I just should mention, just in terms of applications, that in this course when we talk about group theory, we've tended to emphasize these continuous Lie groups. You have rotations, and pretty soon we'll be looking at, in fact, in the next day or two, we'll be looking at the Lorentz group. Group theory tends to be used in a lot of other circumstances. It is quite important in chemistry as well as, other parts of physics, condensed matter physics being one of them, because, symmetries also, you can actually do a lot of derivations regarding molecular vibration modes using symmetry. And of course, if you ever thought that all this stuff looks a whole lot like degenerate perturbation theory, well, you'd be right, okay? Because degenerate perturbation theory is basically saying within that big block diagonal matrix you have, it's an invariant subspace. Plus, another example of the discrete group is actually solving the Rubik's Cube, which after all was invented by a mathematician in order to teach his students about group theory. So, you can see, I think this is actually part of, just part, an enumeration of the multiplication table for a Rubik's Cube. People sometimes write papers on this one too, but not as often as, SU2 double cover or anything like that. Now, another place that you tend to use it, which is kind of related to what I was just talking about here, is this whole thing about the quark model, which I guess you haven't quite gotten to, but you will see. Right? So here we have, well, the guys who invented this, Gell-Mann and Zweig. Yeah. Actually, this is kind of how I tend to remember Gell-Mann. I actually did run into this guy on the elevator one time at Caltech. I was actually going from the basement where all the students, of course, are, right? And at Caltech, they always put the theoretical physicists, they're always on the top floor of the building, sort of closer to heaven was sort of the idea. And the experimental physicists would be sort of like on the fourth floor or something like that. So, I got into the elevator, pressed the 4 button, and he just looked at me and he said, "Wrong floor." Anyway, so, I guess, I have the distinction. Well, I would not be the only person that Gell-Mann ever looked down upon, but that's fine. Anyway, so these guys, these clever guys in the 60s, they were looking at actually diagrams like this. So this is actually this is actually SU2, so you get like these isospin bits here, but then added with another thing, which is the strange quark. Okay, so now you're going from SU2 to SU3. That has a different Lie algebra. Okay, and you can sort of compose your quarks this way, and the Lie algebra gives you a way of categorizing these things. It was actually a group theory argument. Okay, people sometimes forget that, and in fact, it's kind of fun. Even to take someone like Gell-Mann and say, oh, well, what did he think of the quark model? And, right, you can read this little, it takes a little while. The idea that mesons and baryons are made primarily of quarks is difficult to believe, since we know that in the sense of dispersion theory, they are mostly, if not entirely, made up out of one another. Okay? So that is actually, that is the prevailing notion back in the 1960s. So people thought of quarks as more like these currents that are just flowing through the system. But the particles themselves, the idea was that actually these mesons and baryons were actually composed of each other. Okay, it's kind of a weird idea nowadays, but that's what they were dealing with back then. And let's see, right, thus it seems to me that whether or not real quarks exist, the Q and Q bar we've been talking about are mathematical. In particular, I would guess that they are mathematical entities that arise when we construct representations of current algebra. Okay. So obviously in your coursework you're going to find out that's a little bit different, and that's kind of a reminder of something else that a very distinguished theorist wrote in one of his classic textbooks. In the introduction, he says, group theory is a useful technique, but it is no substitute for physics. Okay? So, something everyone should remember, especially since group theory is kind of fun, but it's no substitute. Okay, right, I think that's the end of the recreational period. So just a few minutes left. Well, okay, give you guys an option if thought about any other questions regarding the group theory stuff. Okay. Otherwise, maybe this is, is it the moment that you're waiting for that special relativity will show up again in this course? Okay. All right. Okay. Now we've done the math bit. Okay. Now we're going to get back to that special relativity. Okay. Now we've already gone through the postulates. We do have to relate some of the things that we've been talking about to special relativity now, or maybe the other way. We want to relate special relativity to the math. So let's do a couple definitions. So we have a frame, which is simply a coordinate system with space and time. will also just define an inertial frame as a frame with a constant velocity, with respect to another frame, another inertial frame. Okay? Obviously, the definition is a bit circular, but on the other hand, you can imagine that you yourself, at rest, you are in an inertial frame. Okay? So in other words, from your own inertial frame, you get to extend to all the other inertial frames. Okay, we will now talk about what an event is. This is a point. Okay? But it's a point with space and time. Okay, so sometimes we will talk about this, and I actually find it a little bit easier to talk about these as space-time points. Okay. So oftentimes when we draw diagrams, with these coordinates, right? So let's say we have x as a space coordinate, and maybe we have y as another space coordinate. Now, you might be tempted, of course, just to write t here. Usually what I'm going to do is I'm going to make that c times t. Okay. This is just so that basically the units of your coordinate system are always the same. Okay. So I'm just generally going to work in units of space, or units of length. Okay. So, So if we're talking about Cartesian coordinates, and we'll deal with the contravariant vector, or contravariant components. Obviously, you're going to, using the stuff that we were doing before, you'll write it this way. Okay? In more sort of traditional coordinates, we'll just, relate, conventionally, when we actually give you sort of positions in time, we're going to take them to be, sort of the contravariant components. Sometimes we'll write this as CT, and then we'll just write a little 3 vector here. Okay, just to be a shorthand for those 3 components. Okay. All right. Okay. Now, something on units. Right. I heard a little reference to this somewhere out in the audience. You know where this is going, right? Okay, yeah. C equals 1. Okay. Now, so sometimes this is called natural units. That may not sound that natural to you. It will over time. Okay. Yeah. So let's see. I guess, I think, in general, I'm actually going to try to keep the C's in their proper place. Okay. But sometimes it is just really tedious. Okay. So some of the collision problems that we'll do, they will sort of disappear, probably by mistake. Okay. But in general, I will actually try to put the C's in there. If I'm missing one, just put in as many as you need, okay? Because that's actually the basis under which this works. In fact, just if you're curious, handling, doing dimensional analysis, it's really just another form of group theory. Okay, it's actually just applied group theory. Each one of these is just like, you know, an abelian representation, or a representation of an abelian group. Okay, and yeah, since the reputations don't mix, I mean the representations don't mix, the units don't mix. Okay, and then one other thing that I want to clarify is to distinguish two things which are oftentimes easily confused. Right, so if you had, you know, x and ct here, right, I want to distinguish the event, or generically an event, versus a specific observation event. Okay? I mean, an event as a sort of, you know, as 4 coordinates is just, those are the coordinates that you infer for the event. You may not actually have gotten a signal from it there, you know, from that event at some point. The point at which you realize that something happened, that would be a separate event because you're probably separated in both space and time from the original event. Okay? So it's just, you know, helpful to remember that these two things are different. So as an example, let's see, I think this is quite an old example now, but, right, so at some point this was, let's say this was located at Saturn, okay, and this was, I think, for, okay, so this is actually the Cassini, I think it's the Cassini mission to Saturn, which by the time we observed, right, so this will have the slope of c here, okay, so at the time that we observe on the Earth that we in fact lost contact with the space probe as it was plunging into the Saturn atmosphere, at this point it is, I think, 4:55 Pacific Daylight Time, 15th September 2017, okay? So that's the observation event. From there, we infer that the satellite actually had dropped in at 3:32 PDT, same day. So the difference in time is about 1.5 hours. Obviously, the distance is quite considerable as well. Okay? Anyone want to guess where another important event happens in relation to these? No? Okay. Yeah, some smart aleck in a lecture one time also pointed out that fairly soon afterwards, you have another event, which is called the press conference. Okay, so it happens a little while later, but basically in the same location. Okay. So, you know, these events are oftentimes associated with major scientific discoveries. Okay. So I think, okay, I'm just going to hint at one more thing, but this is all that I'm going to do. It is that we are talking about geometry, and we are going to write the components in this way. So this is the metric tensor for a Minkowski space. Okay, it's clearly non-Euclidean. There is no transformation which is going to make all that can get you from this to one that's purely ones. And yeah, therefore, the length element looks like this. Okay, translating to the same coordinates that I was using back there. Sometimes people will write G mu nu as simply saying, okay, this is a diagonal with this signature, okay? Because I do have to give you a warning, which is that this is the metric that we're going to use in B2 as well as B5. in courses like B4, G mu nu will be opposite. Okay? So between 11 a.m. and noon, for the rest of this term, this is true. From noon to 1, and basically all other time, unless you're a particle physicist, this is true. Okay?